In this example, we will determine the interval of convergence of the sum from n equals 0 to infinity of -2 to the power n over n plus 1 times x minus 3 to the power n. So first of all, what we should do is compare this with the general form of the power series. So the general form of the power series is n equals 0 to infinity. And then we have a sub n times, and then x minus x naught to the power n. And when we compare this, what we see is that our a sub n is equal to this expression right here, right? That is our a sub n. And we see that our x naught is 3. So let's write that down. X naught equals 3. And we found that a sub n equals -2 to the power n over n plus 1. So for theorem 2, we need to look at the ratio of a sub n over a sub n plus 1. So let's figure out what is a sub n plus 1. That is -2, and we're going to replace the n by n plus 1, and then divide that by n plus 1 plus 1, which of course simplifies to n plus 2. So now let's take a look at what rho is. So rho, the radius of convergence, is the limit as n goes to infinity of a sub n over a sub n plus 1, which I can write as follows: the limit as n goes to infinity of a sub n, right? That is this expression here, -2 to the power n over n plus 1. And then we're going to divide that by a n plus 1, which we head over here. So we're dividing that by -2 to the power n plus 1 over n plus 2. And I've replaced the division bar by division symbol to make use of the following property. When you divide two numbers, a fraction divided by a fraction, we can flip the fraction here and change this into a multiplication. Division by fraction is multiplication by its reciprocal. So this is the limit as n goes to infinity of -2 to the power n over n plus 1. And now multiply that by n plus 2 over -2 to the power n plus 1. Right, the plus 1 here. And we can simplify that as follows. That is the limit as n goes to infinity of the absolute value of n plus 1 over n plus 2 over n plus 1, right, times -2 to the power n over -2 to the power n plus 1. And then by the rules of exponents, we can simplify this right here. You would subtract the exponents and you would get negative 2 to the power negative 1, or just 1 over negative 2. So this then is the limit as n goes to infinity of the absolute value of n plus 2 over n plus 1 times 1 over negative 2. And what I'm using here on the side is that when you take the absolute value of a times b, that's the absolute value of a times the absolute value of b. Now the absolute value of negative 1/2 is just 1/2, and that's a constant, so we can bring that outside our limit. So that's 1/2 times the limit as n goes to infinity of n plus 2 over n plus 1. And here I drop the absolute value because n goes to infinity, and so it's positive. Then the limit of this expression, we could use L'Hopital and take the derivative of the top and bottom with respect to n, and then you end up with 1 over 1. So this limit is 1, so we have 1/2 times 1, and that equals 1/2. So that is our radius of convergence. Okay, so now for the interval of convergence, we so far have the following. So on the number line, we mark our x naught. So our x naught is 3, right? That's our x naught. And then we have x naught plus rho and x naught minus rho. So if we add 1/2, then one of the endpoints of our interval is 3 plus 1/2 is 3.5, or 7 over 2. And then the other point would be 5 over 2. So again, this is x naught, this is x naught plus rho, and this is x naught minus rho. And what we need to do is we need to check the endpoints. So that 5 over 2 and that 7 over 2, these need to be checked. So let's take a look at 5 over 2 first. So when we look at x equals 5 over 2, then what is our summation become? Our summation is the sum from n equals 0 to infinity of negative 2 to the power n over n plus 1 times x minus 3. So in this case, we put in 5 over 2, and then we raise that to the power n. And we can simplify that a bit. And so we then have negative 2 to the power n over n plus 1. times -1 or -1/2 to the power n. And when you multiply these two expressions, we can use the following rule for exponents again, that if you multiply a to the power n times b to the power n, that's a times b to the power n. And so -2 times -1, that gives us 1. And so our summation becomes sum from n equals 0 to infinity of 1 to the power n, which is just 1 over n plus 1. Now, this series diverges. It's a p series with p equals 1. And so this diverges. Now, if you plug in x equals 7 over 2, I'll leave it up to you to show that the series simplifies to the following: n equals 0 to infinity for the sum, and then -1 to the power n over n plus 1. And that's an alternating series that actually converges. So this converges. And so the final answer for the interval is that the interval of convergence runs from 5 over 2 to 7 over 2. 5 over 2 is excluded because it diverges there, and 7 over 2 is included. So that is our final answer for the interval of convergence. Now, you will not see any questions like this on the exam. This is just to refresh your memory from something that you have hopefully seen in Calculus 2, and to get a little bit more of a feeling of those power series. Now, when we're going to use these power series to solve differential equations, we'll often refer to the following basic property of power series. So if the sum from n equals 0 to infinity of a sub n times x minus x naught to the power n is 0 for all x in some open interval, then each coefficient a sub n equals 0. So that is something that we'll use in section 8.3. Then here's a short list of known power series. So we typically don't want to reinvent the wheel over and over again when we're looking at power series. So this is a basic list of power series that we can then use to derive other power series, and we'll see some examples in the next section. So the function 1 over 1 minus x has a Taylor series or a power series that is equal to sum from n equals 0 to infinity of x to the power n. The exponential function e to the power x has a power series that runs from n equals 0 to infinity, and each term is of the form x to the power n over n factorial. Sine of x has a power series from n equals 0 to infinity of -1 to the power n over 2n plus 1 factorial times x to the power 2n plus 1. So what you can see when you look at the power series of sine, that it has odd powers of x only. The power series of the cosine is the sum from n equals 0 to infinity, and then each term is of the form -1 to the power n over 2 times n factorial times x to the power 2n. And what you see with the cosine function here, it only has even powers of x. And then finally, in this list, the power series for the natural log of x is -1 to the power n minus 1 over n times x minus 1 to the power n. Now, let's quickly talk about interval of convergence. The first function, the power series, has an interval of convergence from -1 to 1. The exponential function and the sine and the cosine, the interval of convergence is all real numbers. And then finally, the natural log has an interval of convergence from 0 to 2. And what you should notice is that all of the previous ones have power series centered at 0. We can think of x squared, for instance, as x minus 0 squared, x minus 0 cubed, etc. And similar here. But the natural log is centered at 1. So we have x minus 1. And the reason we don't center it at 0 is because ln of 0 is undefined. So again, we'll look at some examples in the next video on how we can use these known power series to derive other power series.